Okay, question 14, parts A through G for the third chapter of Introduction to Statistical Learning. Again, this is a mini-part question, so we'll just tackle them as we go along. Okay, so first we're going to generate some data, x1, x2, and y. Okay, and notice that x2 here is a function of x1, and so what that's going to do is make x1 and x2 pretty collinear. They're going to be highly correlated, and we'll discover that. Run that. And the first question wants us to write out the linear model that is here in our code, and then to point out what the regression coefficients are. So the linear model looks like this, okay, where beta 1, or beta naught, the intercept is 2 here, where beta 1 is also 2, and beta 2 is 0.3. Okay, and there's also an epsilon term here, right here, that is this random component here. And so our norm just gives us 100 variables, or 100 values from a normal distribution with mean 0 and variance and standard deviation 1. Okay. Now we need to look at the correlation between x1 and x2. Remember, like I said, x2 is a function of x1, so they should be pretty highly correlated, and they are. So here's the plot of the data against x1 and x2, and the correlation is 0.84-ish. Okay. And so now we're going to fit a model of y on x1 and x2 and look at the outcome. Okay, and this is what the outcome looks like. And we need to talk a little bit about the results. So, some interesting things here. One is, so we know that the beta coefficients for x1 and x2 are not 0, right? We actually made the data to be not 0 here. But we can only really reject the null hypothesis here with beta 1, not with beta 2, even though beta 2, again, we know that it's not 0. Okay, and then also look at the estimates. Remember that beta 1 should be about 2, and then beta 2 should actually be about 3. Just a quick aside that I'll also address a little bit later. Why should beta 2 be 3? Okay, so if we go back up here to the linear model, we see that we have 0.3 times the x2 variable. But so what is beta, or what is, in fact, maybe I should change that. But what is the beta? The beta is what happens to y, how y changes by a 1 unit increase in that variable there. Okay, and so in fact I am going to change this to 3. But because x2 is on the 1/10 scale here, this coefficient should actually be 3. We should multiply that by 10. Okay, so that should be 3. So I'm going to fix that after I'm done with the video here. Okay. Okay, so on to part D. So now we're just going to regress y on one variable, x1. Okay, and we do that. Okay, and now we see that x1, that the coefficient for x1 is actually pretty close to what we think it should be, about 2, and we can reject the null hypothesis. Okay. And also now for part E, we do the same thing, but now regressing on x2. Okay, and again we see that the beta coefficient gets much closer to where we think it should be, which is about 3. Remember, and here is the p-value, which again suggests that we should be able to reject the null hypothesis. Okay, so now we've seen this thing where when we look at x1, or regress y on x1 and y on x2, we get the values that we know should be there according to the data that we generated up here. Okay, but when we regress both of them together, we get values that do not look familiar to us according to how we generated the data. Okay, so this asks, is there a contradiction here? And explain your answer. So I'm not really sure how to answer whether or not there's a contradiction here. I just explained what the apparent contradiction is, right? Is that that when we include both models, we don't get recognizable outcomes, but when we just look at one, we do. One variable at a time, we do get recognizable outcomes. But I guess that's not really a contradiction because we can explain it, and we can explain it because x1 and x2 are highly collinear. This is just something that happens with highly collinear predictor variables. So now in G, we are going to add an observation to everything. Okay, so on x1 we get this, and x2 we get this, and then the outcome variable is 6. So it's the exact same data plus one more data point. Okay, and we're going to run all the regressions again. And so the first thing I did here was I looked at the correlation again. Okay, so earlier, so here's the correlation. Okay, here's our little outlier way up here. But our correlation should be reduced. So here it's about 0.74, whereas initially it was about 0.84. Okay, so that's expected, right? Okay, so now we have our new model, right, with the new data, and I'm going to look at the summary, and then it also asks us to decide if the new data point is an outlier according to the regression, and whether or not it has high leverage or is otherwise exerting a lot of influence on the fit of the model. Okay, so I've ran all of that. Okay, and so here's my outcomes. Okay, and again, we don't get very recognizable values in the output. Okay, and now we need to decide if the new data point was an outlier or not. Okay, so I'm going to go through these different plots here. So plots 1, 2, and 3, when I use the plot MB function here, the MB is the model. It does not seem that we really have any outliers. Okay, but when we now go to the leverage and residuals, here's our new data point right here. Okay, and so we see that it has fairly high leverage compared to all the other data points, and the residual is fairly high, right? So this new outlying data point is probably exerting a lot of influence over the fit of the model. Okay, so I guess that's our answer there. So now we're going to look at just regressing on x1 with the new data. Okay, so I've done all of that. All right. Now notice that before we added the new data point, our estimate for the beta 1 value was close to 2, and now it is starting to drift a little bit away from that, and that is the effect of the new data point that is possibly an outlier. Okay, and so now we see that new data point 101, is something of an outlier. Okay, it's several standard deviations away from the mean. And here's another view of it in the QQ plot. Okay, it's way up here, way away from where we think it should be. And then when we look at its influence, we notice that it does have a high residual, but its leverage is not great. Okay, compared to everything else in here. Okay, so in this look at the data, just regressing on x1. The new data point is an outlier, but it does not seem to be exerting massive effects on the fit of the line. Okay. Now we do the same thing for x2, and so we run all of that. Okay, now with x2, here's our variable, or here's our our estimate for the beta coefficient. This is close to what we believe that it should be, and now we go through the plots here. And in this view, the new data point does not really seem to be much of an outlier. Okay, and finally we get all the way down here. So even though it is not much of an outlier, it has a high leverage point, but because it does not have a huge residual, it may not be exerting a lot of influence on the final model. Okay, on the fit of this model. Okay, that is it for this one. I should have mentioned that this was all in R. And I will now make one for the Python. Okay.